The night sky, a time machine. The night sky is like a time machine. The further we look into the universe, the further back in time we go. What we see in the sky represents only a tiny fraction of the universe. Most of the universe is made up of dark matter and dark energy. We know they exist, but the universe continues to surprise us. Technology and space exploration. Thanks to advances in technology and engineering, telescopes and other sensors in orbit can provide clearer images without being affected by atmospheric pollution. In the 1960s, satellites began exploring the universe beyond visible light, detecting ultraviolet, infrared, and gamma rays. Research to understand the origin, structure, evolution, and future of the universe is continuously evolving. By the end of the 20th century, the USA and other countries launched larger research programs with space-based telescopes. A dynamic universe. For centuries, people viewed the universe as a static place. However, we now know that the universe is incredibly dynamic. Every moment, a massive supernova explosion is happening somewhere. Scientists aim to develop tools to discover these unpredictable events. Traces of the universe. Satellites like the Cosmic Background Explorer, COBE, and Planck have mapped the microwave background radiation left from the early universe, creating a detailed portrait of the universe's infancy. Since light takes over 13 billion years to reach us, this light provides information about the early universe. These traces are like the fossils of the universe. Echoes of the Big Bang. Around 370,000 years after the Big Bang, plasma consisting of protons and electrons emitted light. As the universe cooled, hydrogen atoms formed, and light began to travel freely. This light has traveled freely since the formation of stars. As photons passed by galaxy clusters, their paths bent slightly. Before reaching the Planck detectors, these photons traveled for 13.8 billion years, allowing us to map the universe. Satellite telescopes and the discovery of the universe. Various satellite telescopes are designed to observe different wavelengths of the electromagnetic spectrum. These telescopes cover near and far infrared light, visible light, ultraviolet frequencies, gamma rays, and cosmic ray detectors. Each of them can reveal the unique structures of stars, nebulae, galaxies, exotic pulsars, and black holes. However, in the public eye, the poster child of these telescopes has undoubtedly been the Hubble Space Telescope. Over its 25 years of service, Hubble has produced some of the most captivating images of the universe, looking back in time through visible and infrared light. Space telescopes and the mysteries of the universe. One of the greatest advantages of the Hubble Space Telescope is its long lifespan, thanks to regular maintenance missions. This has allowed the telescope to study objects over extended periods and make some extraordinary discoveries. Newborn stars launch jets of matter into the surrounding star-forming regions. These jets, known as Herbig-Haro objects, move at supersonic speeds and can be observed to change over very short periods. An image obtained from Hubble can be interpreted in many different ways. But the truly remarkable aspect is Hubble's long-standing contribution to scientific research. For example, when the Horsehead Nebula is examined in infrared light, it reveals its dark secrets and provides insights into its core. The role of Spitzer and infrared telescopes. One of NASA's great observatories, the Spitzer telescope, is an infrared telescope. This telescope allows us to see inside dust clouds in space, discovering star birthplaces known as star nests. During its more than 10 years of operation, Spitzer provided data for over 5,000 scientific papers and opened doors to new results every day. This telescope helped us discover some of the farthest galaxies beyond our solar system and create an ultra-high-resolution map of the Milky Way, enhancing our understanding of our galaxy's structure. Herschel and other infrared telescopes. The European Space Agency's ESA Herschel Space Telescope focused on large star formation regions. Herschel played a critical role in detecting highly embedded young star populations within gas and dust clouds invisible in optical wavelengths. James Webb Telescope, the next-generation tool. The next major space-based infrared telescope is the James Webb Space Telescope, scheduled to launch in 2018. With its 6.5-meter primary mirror, nearly 3 times larger than Hubble's, James Webb is designed to explore the universe's secrets in greater depth. Collaboration of space and ground-based telescopes. Ground-based telescopes also work in the infrared spectrum, providing great complementarity between space and Earth. Images obtained from the Hubble telescope in space can be examined and characterized in more detail using ground-based telescopes. These telescopes capture the light and analyze its spectrum, obtaining crucial data such as redshift in distant galaxies. Ground-based telescopes perform infrared observations that Hubble cannot accomplish for extended periods, allowing observation of how these objects appear in the infrared. This collaboration has enabled detailed examination of supernova remnants and witnessing the birth of stars. X-ray band, a window to black holes for astronomers and cosmologists. One of the most important observational tools in the electromagnetic spectrum is the X-ray band. Every galaxy, including our Milky Way, has a massive black hole at its center. As matter such as dust and gas falls onto this central black hole, it radiates intensely, and these radiations can be observed. If we look at the sky with visible light, we see stars. But when we look with X-rays, we can observe the unique traces of black holes. This way, the X-ray band allows us to better understand the dynamic processes deep within the universe. X-rays and cosmic exploration. By observing the first rays from very distant objects, we can study the cosmic structure of the universe. With this method, galaxies and the active black holes at their centers can be observed over vast distances. This research investigates the distribution of matter in the universe and provides crucial insights into the origin and evolution of the universe. X-ray observations and telescopes. Since X-rays are absorbed by our atmosphere, detectors for these rays must be placed at high altitudes with balloons or in orbit. One of NASA's flagship X-ray telescopes, Chandra, plays a vital role in discovering the dynamic processes of the universe. If you want to find black holes, you need an X-ray telescope. With X-rays, you can observe active galaxies and quasars, which usually contain supermassive black holes. The process of intense matter falling into the black hole at the centers of large galaxies forms the foundation of these processes and makes the galaxy's center bright. The power of Chandra and other observatories. One of the state-of-the-art telescopes, Chandra, with its imaging and spectroscopic capabilities, has enabled scientists to make new and unexpected discoveries. Many scientific studies conducted with Chandra are based on unplanned discoveries. For example, observations with this telescope have allowed us to gain more information about black holes and star-forming regions. NuSTAR, Sharp X-ray Observations. One of the latest X-ray telescopes, NuSTAR, focuses on X-rays to provide much sharper images. One of the primary scientific goals of this telescope is to take a full census of black holes in the universe. This helps us better understand the distribution and density of black holes in the cosmos. X-rays and gamma-ray observations. X-rays have revealed explosive processes and nova eruptions that can only be seen at these wavelengths. These observations have been crucial in understanding the dynamic nature of the universe. The European Space Agency, ESA, has the XMM Newton telescope to study cosmic evolution. This telescope plays a unique role in uncovering the unknown structures of the universe. Additionally, ESA's International Gamma-Ray Astrophysics Laboratory, Integral, is used to discover new gamma-ray sources and study gamma-ray frequencies. This telescope makes significant contributions by helping us understand the energetic and extraordinary processes in the universe. The importance of integral and gamma-ray observations. Integral is one of the few satellites that study gamma rays and is of great importance. Gamma-ray observations help us understand the evolution of stars in the universe. Working together with other satellites and observatories around the world, we can create a complete picture of how these stars evolve. However, without integral, we would miss a crucial piece of this vast puzzle. Distribution of elements in the universe. Integral helps us understand how stars disperse different types of materials into the universe. Supernova explosions are the sites where elements in the universe are produced. We are made of these elements produced by supernovae. Therefore, understanding the source of life and how it forms is vital for these observations. The power of gamma rays. Gamma rays sit at the top of the electromagnetic spectrum and carry the most energetic photons. These rays come from black holes, exploding stars, and even the Sun. Integral provides crucial insights into the dynamic structure of the universe by studying these powerful gamma ray sources. Fermi Gamma-Ray Space Telescope and SWIFT. Originally known as GLAST, the Fermi Gamma-Ray Space Telescope observes the entire sky with high-energy gamma rays every 3 hours, creating the most detailed map of the universe at these energies. When it detects a new gamma-ray burst, it collaborates with the SWIFT satellite. SWIFT can quickly rotate in the sky and direct its X-ray telescope, optical, or ultraviolet telescope to the location of the gamma-ray burst. Fermi is designed to take data from the upper end of SWIFT's energy range and extend it to much higher energies. The higher the energy range, the more exotic and unusual the observed objects become. SWIFT and Fermi operate differently. SWIFT is more agile and small, targeting specific objects, while Fermi continuously scans the entire sky. Therefore, when something interesting is detected with Fermi, SWIFT can be asked to use its additional telescopes to gather more detailed data. Cosmic rays and the alpha magnetic spectrometer. Another type of radiation studied in orbit is cosmic rays. The 8-ton alpha magnetic spectrometer, AMS, attached to the International Space Station, is designed to analyze cosmic rays. These rays consist of protons, alpha particles, atomic nuclei of heavy elements, electrons, antimatter particles, positrons, and gamma rays. Studying these particles can answer fundamental questions about the mysterious absence of antimatter and the nature of dark matter in the universe. Calibrating positrons accurately is essential because when dark matter collides with another dark matter particle, positrons are produced. The properties of positrons can provide clues about the origin of dark matter. The mystery of dark matter. About 80% of the universe's matter is made up of dark matter, which cannot be directly observed by telescopes. Dark matter does not reflect, absorb, or emit light. However, it can be inferred to interact with matter through the gravitational effects observed in the orbital speeds of stars around galaxies and the movements of galaxy clusters. Despite decades of research and effort, the true nature of dark matter remains a significant mystery. Dark matter, cosmic web, and the expansion of the universe. This visualization shows the formation of large-scale filaments in the universe and the image of the cosmic web resulting from the collision of galaxies made up of gas, stars, and dark matter. Dark matter is thought to form the framework of this web. Galaxy clusters are the largest gravitationally bound structures in the universe. The expansion process of the universe after the Big Bang, it is believed that the initial expansion of the universe slowed down but later began to accelerate. A space telescope built by ESA, with a planned launch date in 2020, aims to map the impact of dark matter and dark energy on the universe. This telescope is part of the Euclid mission, which aims to map the universe. Mapping dark matter structures and determining the properties of dark energy are crucial for understanding the future of the universe. The increase of dark energy. Interestingly, as the universe expands, the amount of dark energy also increases. This is because ordinary matter, dark matter, and normal matter dilute as they expand. However, dark energy becomes more dominant proportionally in the expanding universe. This leads to an increasing impact of dark energy as the universe reaches a larger volume. Weakly interacting massive particles, WIMPs, the most popular particle physics model for dark matter, is based on weakly interacting massive particles, WIMPs. WIMPs move through the universe almost without colliding with anything or each other. The idea of two WIMPs merging to produce gamma rays is likened to bullets crossing paths in a crossfire. The density around a massive black hole increases the likelihood of these events occurring. Such gamma ray emissions can be detected with gamma ray telescopes. Black holes and dark matter, theoretical simulations. In a theoretical study, Schmidtmann's computer simulation examines dark matter particles around a rotating massive black hole. All movement occurs near the black hole's event horizon, where nothing can escape, in a flattened region called the ergosphere. Within the ergosphere, the black hole's rotation drags spacetime along, forcing everything to move almost at the speed of light in the same direction. These fast-moving, dense dark matter particles collide to produce gamma rays. However, only a portion of this high-energy light can escape the black hole. On the side where the black hole rotates towards us, we can see the gamma ray glow at higher energy. Simulations provide important information indicating that upcoming gamma ray telescopes will be able to detect these astrophysical signals. Dark matter and black holes, a poetic encounter. It is quite impressive and almost poetic that two of the most enigmatic phenomena in the universe, dark matter and black holes, come together to explain each other. These studies can provide critical insights into the nature and functioning of the universe. Future missions and research. Gravitational Wave Observatory. Future missions will deploy an observatory to study gravitational waves and test Einstein's theory of general relativity. Athena mission. Planned to launch in 2028 by ESA, the Athena mission will map hot gas structures and investigate supermassive black holes. Sloan Digital Sky Survey, SDSS, one of the most ambitious astronomical projects to date, aims to create a three-dimensional map of about 1 million galaxies and quasars. Large Hadron Collider and the Mysteries of the Cosmos, recently refurbished and upgraded. The Large Hadron Collider, LHC, is one of the tools that can help explain the structure of the universe. This collider conducts studies to understand dark matter and the fundamental building blocks of the universe by investigating weakly interacting massive particles, WIMPs, and other exotic particles. Perhaps in the future, scientists, astronomers, and engineers will turn their attention to deeper questions and mysterious theories offered by particle physics. These include topics like multiple dimensions, other universes beyond our own, and phenomena beyond the event horizon. Such studies and theories could become new scientific frontiers in the future. As humanity progresses in these areas, we will take a step closer to unraveling the deepest secrets of the cosmos.